Hello everyone, Assalamualaikum warahmatullahi wabarakatuh and good day to every one of you. Welcome to my video. So basically this is a continuation of a lecture video for chapter on transformer. Okay, so my name is Dr. Norzulaili binti Muhammad and here is my email address. So you can just feel free to email me whenever you have a question regarding the content of this video. Okay. So in this video we are going to cover the last two subtopics of the chapter, which is subtopics on autotransformer and also subtopic on the three-phase transformer. Okay, so basically for the autotransformer we will see what is the concept of the autotransformer. Okay, so why do we need the autotransformer and also the advantage and disadvantage of the using of the autotransformer. Okay, and then for the three-phase transformer we are going to see on how to construct the three-phase transformer using the three-phase transformer bank, and then we will see the various type of configuration for the three-phase transformer bank, and also we are going to solve the problem related to the three-phase transformer. Okay, so let's move to the first subtopics, which is autotransformer. Okay, so basically this is an example of autotransformer that available in the market. Alright, so this is the equivalent circuit diagram for the autotransformer. So what is the autotransformer actually? So the autotransformer is a special connection of the transformer from which a variable AC voltage can be obtained at the secondary side. Okay, so you can have a variable AC voltage at the secondary side by changing the secondary winding. Okay, the special connection of the transformer where a common winding is mounted on the core and secondary winding is taken by tapping the winding. Okay, so here is the common winding that mounted on the core, and then the secondary winding will be tapping at the existing winding here. Okay, this means that the primary and secondary of an autotransformer are physically connected. However, the basic principle of operation of the autotransformer is similar as the two-winding transformer, where you can still use the general equation of the two-winding transformer, where V1 over V2 will be equal to N1 divided by N2 equal to I2 divided by I1, and then this is equal to the A, where A is a turns ratio. So in order to prove that the autotransformer is fulfilled the ratio, we need to consider an autotransformer below. Okay, so you have the autotransformer circuit just like this. Okay, and then MMF at the point of A, B will be given by Ni. Okay, so you know MMF will be equal to Ni. So in this case, N is equal to N1 minus by N2, because you want to have a N from A until B, so N will be equal to N1 divided by N2 multiply with the I is a I1. Okay, I1 is the one that flowed through the line AB. Okay, so that's why here you have N1 minus N2 multiply with I1. Okay, and then we can rearrange the equation so that we have N1 I1 minus N2 I1. Okay, and then you also know that A will be equal to N1 minus N2. So we can rearrange so that we have N2 will be equal to N1 divided by A. Okay, and then after that we can substitute this equation into here. Okay, we substitute N2 will be equal to N1 minus divided by A. So you have N1 I1 minus N1 divided by A multiplied with I1. Okay, alright, so this is considered as equation number 1. Next, MMF at the point BC. Okay, you know MMF is equal to Ni, so N will be equal to N2. Okay, because from B to C, N will be equal to N2. And then for the I that flowed through the BC is equal to I2 minus I1. Okay, alright. And then after that, we can rearrange the equation so that we substitute N2 is equal to N1 divided by A. So I just substitute here N1 divided by A multiply with I2 minus I1. Okay, so this is considered actually as a equation number 2. Okay, equation 1 will be assumed to equal to equation number 2. Okay, and then finally you have N1 I1 minus N1 over A multiplied with I1 equal to equation 2, which is N1 divided by A multiplied with I2 minus I1. Okay, alright. And then after that, we can cancel this thing here, and also N1 divided by A multiplied with I1. So here and here can be cancelled. So finally, I have N1 I1 equal to N1 divided by A multiplied with I2. Okay, so N1 and N1 we can cancel out. So finally, we have I1 equal to I2 divided by A. So A is equal to I2 divided by I1. Okay, so it is proven that the operation of the autotransformer is same as per operation of the two-winding transformer. Okay? Okay, next we will see the advantage of using the autotransformer connection. Okay, so because of the autotransformer connection is physically connected between the primary and also the secondary winding, so that's why it has a lower leakage reactance, and it also have a lower losses, lower exiting current, okay, and it can also increase the kVA rating. Okay, and then by using the autotransformer, you can also have a variable output voltage by changing the tapping at the secondary winding. Okay, however, the disadvantages of using the autotransformer connection is due to the direct connection. Okay, because when you have a direct connection between the primary and the secondary winding, so it means that there is no isolation between the primary and also the secondary part. Okay, next we go to the second subtopic, which is three-phase transformer. Okay, so basically the three-phase system is used to generate and transmit massive electrical energy. The three-phase transformer are required either to step down or step up voltage in the various stage of power transmission. And then the three-phase transformer can be built in one of two ways. Okay, either by connecting a bank of three different single-phase transformer, or you can also construct the three-phase transformer on a common magnetic structure. Okay, so basically in this video we will be focusing only on the how to connect a bank of three single-phase transformer. Okay, for the three-phase transformer bank, so basically this is the example of a configuration of a three-phase transformer. Okay, three-phase transformer bank is actually a set of three similar single-phase transformer that connected to form a three-phase transformer. Okay, so meaning that now you have single-phase transformer, you have three different single-phase transformer, and then you combine it together to form a three-phase transformer. Okay, so if you refer to here, this is example of a transformer that this is a one single-phase transformer, second single-phase transformer, then this is the third transformer. Okay, and then you just combine all those three to make it become three-phase transformer. Okay, the primary and also the secondary winding may be connected in either Y or delta configuration. Okay, so in this case, the primary is connected as a Y connection, and the secondary side is connected as a delta connection. Okay, you can see here that on the primary side, the three terminal here, 1, 2, and 3, okay, the same terminal here is connected to each other to form the neutral of Y connection. Okay, on the secondary side, the winding are connected in series to make it become delta connection. Okay, there are 4 different possible configuration of the three-phase transformer. Okay, the first one is the Y delta. Okay, meaning that at the primary side you have a Y configuration, and at the secondary side you have a delta configuration. For Y delta configuration, it is commonly used to step down a high voltage to a low voltage. Okay, for the delta Y configuration, okay, meaning that at the primary side you have a delta, and at the secondary side you have a Y connection. Okay, it is commonly used to step up voltage from lower to the higher voltage. Okay, And then there are also configuration of delta delta, okay, meaning that here you have a delta connection, here also you have a delta connection. Okay, for the delta delta connection, we also known it as a open delta or V connection, okay, in which this connection have the advantage that one of the transformer can be removed for repair, and the remaining of two, okay, let's say you can just remove one transformer for repair, and the remaining two can still deliver the three-phase power at the reduced rating. Okay, so this is a special case of a configuration. Okay, and then the last configuration is the YY connection. Okay, so this connection is actually rarely used due to the problem with the exiting current and induced voltage. Okay. Okay, so the three-phase transformer connection can also be represented by this diagram. Okay, so basically this represent the Y delta connection of the three-phase transformer. Okay, so basically the primary here is considered as a primary winding, and here is considered as a secondary winding. And then the primary and secondary winding shown parallel to each other belong to the same single phase transformer. Okay, meaning that here and here is parallel, so meaning that here and here represent to the same single phase transformer. Here and here is parallel, so meaning that here and here represent to the same single phase transformer, and here represent to the same single phase transformer. Okay, and then the primary and the secondary voltage and also current are also shown here. So this is considered as a primary voltage, and this is the primary current, and here is the secondary voltage, and here is the secondary current. Okay, and then the turns ratio is given by A is given by the turns ratio, where A is equal to N1 divided by N2. Okay, so other possible connection is shown as here. Okay, this is considered as a delta delta connection. Okay, meaning that here you have this one and this one refer to the same single phase transformer. This and this refer to the same single phase transformer, and here refer to the same single phase transformer. Okay, okay, so this is for delta delta connection. Okay. This is example for the topology of a delta Y connection. Okay, so this is a delta connection at the primary side, and also the Y connection at the secondary side. Okay, and then this is the last topology of the three-phase transformer connection, where you have a YY connection. Okay, Y connection at the primary side and Y connection at the secondary side. Okay, so remember this connection is rarely used because of the problem with the exiting current and induced voltage. Okay, so usually this is the special this is the one that we always use, which is can use to step down the voltage, and this is used to step up the voltage. Okay, now we go to the topics on single phase equivalent circuit, or we call it as a SPEC. Okay, so basically the single phase equivalent circuit can be used in order to do analysis on the three-phase transformer, provided the three transformers are identical to each other and the source and load are balanced. Okay, so let's say you have this condition where the three transformers are identical and the source and load are balanced. So you can just do the analysis based on the single phase only. Okay, so this is considered is sufficient enough in order to determine the variable on the two sides of the transformer. Okay, so in order to determine the value of the in order to determine the parameter on the primary side and also the secondary side of the transformer, you can just only focus on single phase analysis only, rather than do the analysis on three different phase. Okay. The single-phase equivalent circuit can be conveniently obtained if all source, transformer winding, and load impedance are considered to be Y-connected. Okay, meaning that now, let's say you have a configuration of delta to Y, so meaning that you need to convert the delta connection to be Y-connected first. Okay, So you need to change all the connection to be Y connected. Then only you can retrieve the single phase equivalent circuit. Okay, so basically, this is how you do the source transformation from delta to Y connected. Okay, so for example, you have a combination of delta Y. So at the primary side where you have a delta connection, you need to transform the source to become the Y connection first. Okay, so basically for your Vy, which is for your the value of voltage for your Y configuration will be equal to V phase on the delta divided by square root 3. Okay, so this is how you do the source transformation from delta to Y configuration. Okay, for the impedance transformation, let's say, for example, you have a combination of three-phase transformer of Y delta configuration, meaning that you have a delta connection at the secondary side. Okay, you know that the secondary side will be connected to the impedance, connected to the load. Okay, whenever you have a load configuration of delta like this, okay, you need to change delta to Y connected first. Okay, so the value of ZY will be equal to Z phase divided by 3. Okay, so this is how you do the impedance transformation from delta to Y connected. Okay. Okay, so basically this diagram shows you on the step-by-step on how to get the spec. Okay, so this is the single phase equivalent circuit based on the three-phase configuration. Okay, so let's say here you have a three-phase transformer connected, three-phase transformer configuration where you have a Y and delta topology. Okay, and then first of all, you need to change first from delta to Y. Okay, so you need, since the primary already in Y, but at the secondary you have a delta configuration, you need to change from delta to become Y first. Okay, so at the secondary winding, from delta, you change it to become Y. Okay, same goes to the load. From this topology, you change to become Y. Okay, and once you have a Y and Y configuration, then only you can come up with the spec, which is single phase equivalent circuit. Alright. Okay. So the turns ratio for each of the single phase transformer, we consider it as a A. Okay, where A is equal to N1 divided by N2. Okay. However, the turns ratio of the three phase transformer is a A prime. Okay, so there will be 4 different formula for the A prime. Okay, so usually for, let's say you have a topology of Y to delta, so A prime will be equal to square root 3 multiplied with A. And then if you have a topology of a delta to Y connection, so this is the formula of the A prime, where the turns ratio of the three-phase A prime will be equal to A divided by square root 3. Okay. Let's say you have a topology of delta delta, so A prime will be equal to A, and same goes to the YY configuration. A prime will be equal to A as well. Okay, alright. Okay, for the voltage and current in three-phase circuit, so basically there are two values to be considered. What the phase value and also the line value. Okay, so remember, the phase value and line value is not same, where let's say you have a star connected like this. Okay, so this is star connection, where here is your I line. Okay, in this case, I line will be equal to I phase. Okay, so here I phase, here you also have a I phase, I phase. In this case, I line will be equal to I phase. However, V phase, okay, V phase meaning that from the line to the neutral. Okay, so this is the V phase. This is the V line from first line to the second line. Okay, so the V phase will be equal to V line divided by square root 3. Okay, or you can also rearrange it also, so that you have V line equal to square root 3 multiplied with V phase. Okay, so in this case, for the star connected, the line voltage lead the phase voltage by 30 degree. Okay, and then for the delta connected, so basically this is your one phase, second phase, this is third phase. Okay, so the current that go through here, we call it as a I phase, but here we call it as a I line. So in this case, I phase not equal to I line. But here at star, I phase is equal to I line, right? Okay, so in this case, I phase not equal to I line. Okay, I phase is equal to I line divided by square root 3. Okay, but V phase, which is from this point to this point, is equal to V line. Okay, for delta connected, V phase equal to V line. Or you can also rearrange this equation to have I line equal to square root 3 multiplied with I phase. Okay, for a case of delta connected, the line current, lead the phase current by 30 degree. So in this case, V line lead the phase voltage by 30 degree. Alright. Next, for the three-phase power equations. Okay, so the equation for the real and active power for the three-phase will be equal to 3 multiplied with V phase, I phase cos theta. And then for the reactive power of three-phase will be equal to 3 multiplied with V phase, I phase, sin theta. Okay, for the apparent power of the three-phase will be equal to 3 multiplied with V phase, I phase. Or, however, for the line quantities, let's say you have a V line and I line. So, this is the equation where you have a P for the three-phase will be equal to square root 3 multiplied with V line to line multiplied with I line cos theta. Or for the reactive power of three-phase will be equal to square root 3 multiplied with V line to line multiplied with I line sin theta. Or for the apparent power of the three-phase will be equal to square root 3 multiplied with V line to line multiplied with I line. Okay? Okay, now let's have a look at the following example on how to solve on problem on the three-phase transformer. Okay, the question here, you consider you have a three set of a single phase transformer with the S rated of 50 kVA, and then the turns ratio is a 2300 to 230 volt. 6 phase transformer are connected to form a three-phase transformer with 4000 step down to 230 volt transformer bank. Okay, so basically this is the this is the input voltage to your three-phase transformer, and then this is the output voltage of your three-phase transformer. Okay, so this is considered as a step down voltage. The equivalent impedance of each of the transformer referred to the low voltage side is given by this. Okay, so here refer to the low voltage side, meaning that refer to the secondary side. The three-phase transformer supplies a three-phase 120 kVA, 230 volt, 0.85 power factor lagging load. Okay, meaning that now the three-phase transformer, okay, the combination of the single phase become three-phase. So the three-phase transformer will be supplied to this load. Okay, alright. So the question here, draw the schematic diagram showing the transformer connection. And then you need to determine the transformer winding currents. And then we need to determine the primary voltage in terms of line-to-line voltage that required to produce this configuration. Okay, and then for D, you need to determine the voltage regulation. Okay, so for the solution, number A, you need to draw the schematic diagram that show the transformer connection. So in this case, you know that based on the question, the primary is connected to 4000 volt, and then the secondary is connected to the 230 volt. So this is considered as a step-down transformer. So remember, for the step-down transformer, the topology is a Y delta configuration. Okay, so this is how you draw the circuit diagram. So where you have a Y topology at the primary winding, and then you have a delta topology at the secondary winding. Okay, so this 4000 is the value of the V line to line at the input side, and then the 230 volt is the V line to line at the secondary side. Okay, and then based on the question also, it said that the three-phase transformer is connected to the load. Okay, so the parameter of the load is a three-phase load where the S rated is 120 kVA and with power factor 0.85 lagging. Okay, so basically IS I secundar is represent the I line, okay, and then this is the I2. I2 represent the winding current at the secondary side. Okay, for I1 represent the primary current at the the winding current at the primary side. Okay, and then V1 represent the voltage at the primary winding. Okay, and then IP represent the I line at the primary winding. Okay, and then for B, you need to determine the transformer winding current. So in this case, based on the circuit that you draw just now, the winding current represent the I1 and also I2. Okay, alright, so how to calculate that? So basically, based on the power equation, you know that S will be equal to square root 3 multiplied with V line to line multiplied with IL. Okay, so in this case, if we refer to here, okay, since we know that the S at the load is given by 120K, okay, so here you have a IS. IS represent the I line, okay, so and then this is your V line to line. Then you can find the value of IS. In this case, IS is the I line. Okay, IS is the I line. So IS will be equal to S divided by square root 3 multiplied with V line to line. Because we know the value of V line to line is 230. So you just key in the value here, 120K divided by square root 3 multiplied with 230. So you get IS, which is your I line, will be equal to 301.24 ampere. Okay, so once you find the value of IS, then you can find the value of I2. I2 is the winding current at the secondary winding. Okay, so you know your I2 is, in this case, is the I phase, right? So I phase, you know that I phase is equal to I line divided by square root 3. So this is the formula that you must memorize. Okay, so I2 will be equal to I line divided by square root 3. So I line is IS. So 301.24 divided by square root 3 is equal to 173.92 ampere. So this is the winding current at the secondary winding. And then how about at the winding current for the primary winding, I1? Okay, so you can use the formula using the turns ratio. Okay, first you calculate the turns ratio A. A will be equal to, for the single phase transformer, okay, for the single phase transformer is equal to 2300 divided by 230 equal to 10. Okay, and then you know, by using the formula A will be equal to I2 divided by I1. From here, you can find the value of I1. Since you know the value of I2 already, you know the value of A, then you can find the value of I1. Okay, I1 will be equal to 173.92 divided by 10. So, I1 is equal to 17.39A. Okay, so now you had determine the transformer winding current. This is your I2 and this is your I1. This is winding current at the secondary winding. This is the winding current at the primary winding. Okay, next question number C. You need to determine the primary voltage. Okay, so in this case, the primary voltage is the V1. Okay, but the value of V1 must be line to line. Okay, so based on the load value, you know that the power factor is equal to cos theta. Okay, so the cos theta is given by 0.85 lagging. So you can find the value of theta. So theta will be equal to cos negative 1 multiplied with 0.85. Okay, so you know that theta will be equal to, because here lagging, so that's why you have a negative sign here. So negative 31.8. Right, and then so the I1 that you get in the previous slide, I1 will be equal to 17.39 angle negative 31.8. Alright, so this is the value of I1. Okay, so next, you need to transfer the equivalent impedance from secondary to primary side. Okay, so you know from the question, it gives you the value of the equivalent impedance that refer to the secondary side. So this is the value refer to the secondary side. Now we need to transfer the equivalent impedance from secondary to primary. Okay, so you know that how to get it. You can just multiply the Z equivalent that refer to the secondary, multiply with the A squared, then you can get the value of equivalent impedance refer to the primary side. So in this case, A squared is 10, 10 squared is 100, so 100 multiplied with the equivalent impedance that refer to the secondary side. So you get the value of equivalent impedance refer to the primary side. Okay. And then the single phase equivalent circuit will be given by this. Okay, so this is your V1 because you refer to the primary side. So that's why here you have a V1. Okay. Why you need to refer to the primary? Because here you need to find the V1. Okay, so V1 is referred to the is represent the primary voltage. So that's why I transfer my circuit so that we have a value refer to the primary side. Okay, so V1. So this is the equivalent impedance that we transfer from secondary to primary side. So here 1.2 plus J 1.6 ohm. Here you have a 1.2 J 1.6 ohm. Okay, and then you know here is the I1. Okay, and then this is the V2 prime. Okay, so V2 prime is equal to 2300 volt. Okay, and then based on the circuit, based on the single phase equivalent circuit, we can apply the KVL. Okay, so apply the KVL. From this point, you have negative V1 plus I1 multiplied with the Z equivalent refer to the primary side. Okay, plus V2 prime. Okay, and then we can rearrange it so that we have V1 equal to I1 Z equivalent 1 plus V2 prime. Okay, and then we can just substitute the value of I1. I1 is given by this. Okay, and then Z equivalent 1 is referred to here. Okay, alright, plus V2 prime is equal to 2300 phase of 0. Okay, so finally you get the V1 will be equal to 2332.4. Okay, so this is the V1, but it is in terms of phase voltage. Okay, so remember the question asks you the value of primary voltage in terms of line to line voltage. So you need to convert from V phase to V line to line. Okay, so you know V line to line will be equal to square root 3 multiplied with V phase. So square root 3 multiplied with this value, you get 4039.8 volt. Okay, so this is the primary voltage line to line required by the three-phase transformer. Okay. And then the last question, you need to determine the voltage regulation. Okay, so basically this is the formula of the voltage regulation for the case that referred to primary. Okay, so since you have a circuit that refer to the primary, so you can just use this formula. Okay, so voltage regulation will be V1 minus V2 prime divided by V2 prime. So in this case, V1 you get in the previous slide, V1 is equal to 2332.4. So this is the V phase. Okay, V phase of the V1 minus 2300 divided by 2300 multiply with 100%. Okay, so the voltage regulation we get is a 1.41%. So basically, if the value is nearer to 0, so meaning that the voltage regulation is a very good value. Okay, alright. Okay, now we go to the second example of the three-phase transformer problem. Okay, so in this question, it said that you have a three-phase load. So this is the parameter on the load. Okay, so the three-phase load is supplied by the three transformer that connected in Y delta configuration by means of a common three-phase feeder whose impedance is given by this. Okay, so meaning that the transformer is connected to the load through this three-phase feeder. And then the transformer also are supplied from the three-phase source through a three-phase feeder whose impedance is given by this. Okay, so meaning that between this, you have a source, and then the source connected to the feeder, then only connected to the transformer at the primary winding. Okay, and then the secondary winding of the transformer connected to the feeder, then the feeder connected to the load. Okay, and then the equivalent impedance of the one of the transformer referred to the low voltage side is given by this. Okay, so in this question it said that refer to the low voltage side. So in this case, low voltage refer to the secondary side. Okay, and then the question asks you to determine the required supply voltage if the load voltage is 230 volt. Okay, so given the V2, which is the load V2 of meaning that the secondary winding secondary voltage is given by 230, you need to find the primary voltage, which is the supply voltage. Okay, the solution here, step number 1, first of all, you need to draw the 3 set of the single phase transformer with all the information above. Okay, because you know, based on the data, it is the step down voltage, and then it also said from the question that it is a Y delta configuration. Okay, so that's why you need to draw the Y delta transformation. Okay, so this is the 3-phase transformer. Okay, so the transformer is connected to the supply and connected to the load through the feeder. Okay, so here you have a feeder, and here also you have a feeder. Okay, and then the voltage of the load is given by 230 volts. So this is the V line to line. Okay, and then you need to find the value of the V supply here. Alright, okay. So step number 2, you need to get the equivalent circuit of the individual transformer that you need to transform from secondary side to the primary side first. Okay, so how to get the value of the equivalent circuit? So you just need to multiply with A squared, because now you want to transfer from secondary to primary. Okay, so multiply with A squared. Okay, so in this case, A is given by your V1 divided by V2. So V1 is 1330 divided by V2 is 230. Okay, so the transformation ratio by the basically given by this value. Okay, alright, so 1330 divided by 230. Okay, so this is the A, and then A squared multiplied with the Z equivalent 2. The Z equivalent 2 is actually the impedance equivalent referred to the secondary side. Okay, so you get the value of impedance equivalent circuit that refer to the primary side. Okay, and then after that, you need to calculate the turns ratio of the equivalent Y delta bank. Okay, so the turns ratio is given by A prime equal to square root 3 multiplied with A. So here is your A, just multiply with square root 3, you get A prime is equal to 10. Okay, so based on that, you can, and then after that, you need to convert the secondary to Y connection. Okay, so you know, previously, you have a combination of Y to delta combination. So in this case, you need to convert from Y to Y. Okay, so in this case, the secondary winding become Y connected already. And then the load also, you need to change it become Y connected. Okay, alright. So if you refer to here, this is the V line to line value, 230. Okay, so once you change it to become Y connected, so here is your V phase. So V phase will be equal to V line divided by square root 3. Okay, so 230 divided by square root 3 is equal to V phase here is equal to 133 volt. Okay, and then next, step number 4, draw the single phase equivalent circuit. So this is the single phase equivalent circuit where you have a V supply, and then you have this is the value of the feeder. Okay, and then this is the value of the equivalent circuit that refer to the primary side. Okay, and then this is your winding of your 3-phase transformer. Okay, where your A prime is given by square root 3A, so the A prime is equal to 10. Okay, so this is the value of your feeder at the load. Okay, so this is your load, where your VL is equal to 133 angle of 0. Okay, and then after that, you need to refer everything to the secondary side, and then you combine with the secondary feeders. So this value and this value, we need to refer to the secondary side, and then we need to combine with the secondary feeder value. Okay, so the Z equivalent 2, meaning that the Z equivalent that refer to the secondary side will be equal to 0.8 plus J5 plus 4.01 plus J8.36. You need to divide by A prime square root. Okay, so A prime is given by 10. Okay, plus these two value. Okay, so you just use your calculator, you can get the Z equivalent 2, meaning that all the value that refer to the secondary side will be equal to 0.051 plus J 0.149 ohm. Okay, so based on your single phase equivalent circuit, you know that the load current, which is IL, is equal to the line current on the secondary winding. And the IL can be obtained from the data on the load given. Okay, so based on the power equation, you know, your F prime power is equal to square root 3 multiplied with V line to line multiplied with I line. So your I line, which is your load current, is equal by 27K divided by square root 3 multiplied with your V line to line, which is 133. Okay, so your I line is equal to 67.67 ampere. Okay, so the angle for the IL is given by the power factor value. So power factor is 0.9. So cos theta is equal to 0.9. So you can just use your calculator to get theta will be equal to 25.8. Alright, so remember, because of the power factor is lagging, so that's why the theta will be negative. Okay, and then therefore the equivalent circuit referred to the secondary side is given by this. Okay, so the V supply is referred to the secondary side, so that's why you have Vs prime. This is the value of equivalent impedance that refer to the secondary side, and then this is your IL and this is your VL. Okay, so here your IL is given by 67.67 angle negative 25.8. Why negative? Because the power factor is lagging. Okay, and then based on the circuit that refer to the secondary side, then you can apply your KVL in order to get the value of V supply prime. Okay, so the V supply prime will be equal to IL multiplied with the Z equivalent to plus your VL. Okay, so you apply KVL at this loop, so you get this equation. So you just key in all the value accordingly, IL, Z equivalent to, and VL. So finally you get your Vs prime will be equal to 140.7 angle 3.1. Okay, here is Vs prime actually. Okay, so this is Vs prime. And then the question asks you the required supply voltage of Vs. So based on the Vs prime, you can convert it become Vs using the formula. Okay, so Vs will be equal to A prime multiplied with Vs prime. So in this case, A prime is 10. So 140.7 multiplied with 10 is equal to 1407 volt. Okay, and then finally, this is the phase value. And then you need to convert into line to line value. So line to line value is square root 3 multiplied with 1407. Finally, the value is equal to 2437 volt. Okay, alright. So that's how you calculate the required supply voltage for the transformer. So that's all for now. Thank you for watching my video. Thank you for your time. I'll see you in my next video. Okay, bye.